All right, cool. Yeah, thanks very much for organizing this lovely session. Two things. I'm not an ultra-fast guy, so I'm in the other half, basically ultra-slow stuff. But hopefully try to introduce to you materials, geometries, and some phenomenon that would be sorry, relevant for this audience. And apologies that I didn't think it made sense for me to try to give a dynamics tutorial. So I will, anyway, it is what it is. So I hope you'll be entertained. So I'm going to tell you a little bit about some interesting developments in materials towards this community and basically walk you through 3 examples of materials by design or attempts at materials by design that hopefully you'll find interesting. So, yeah, look, this is really based on a huge number of important collaborations. I won't try to read through them all, but you can see across all different experimental modalities and theory that's been essential. I'll just try to highlight the young people that led the different aspects of the work as we go forward. So yeah, I want to go through 3 stories, if you will. And the first one is probably familiar to many of you if you're coming from the correlated world. And that is this long-standing notion almost immediately after the discovery of cuprate superconductors, whether there would be other materials. You know, it was such a strange place to find superconductivity, not to mention high-temperature superconductivity, that might have similar instabilities and opportunities. And various layered nickel oxides and heterostructures have been long a target for this agenda. And that's really the backdrop of some of the things in the first kind of vignette I would like to tell you about. And so at least some of the important ingredients is that you're dealing with a quasi-2D system, spin 1/2 antiferromagnetic lattice that you can chemically dope in various ways. And so can we have this kind of opportunity in different materials families? So specifically, if we look at a layered nickel oxide, we'll take this so-called infinite layer structure of the cuprates, and the question boils down to whether you can make a monovalent nickel in this layered format. And why this would be interesting is that this would give you 9D electrons, so it would be a nominally similar electronic structure, and might be an interesting playground to extend the opportunities found in the cuprates. And so all through the early 90s, for those of you who know the 214 nickelate story, that was partly motivated by this. And there were a number of theory discussions of this opportunity. I pick one from Warren Pickett about 15 years before we made progress on the experimental side, just showing you the LDA limit of electronic structure here. The first point is you have this large dx squared minus y squared type kind of band. Much like you have in the cuprates. But as you can see by his title, the point was that you have an additional feature, which you have hybridization between, let's say, the rare earth 5D states and the nickel 3D states. And so you have additional electron pockets, and this is kind of a self-doped system. And so this is one of the things that is an interesting twist on this problem. Okay, so for the materials half of you, if I say nickel 1+, that's very strange. And indeed, this is not something, as far as we know, it is thermodynamically stable. Okay? And actually, we're relying on some really creative chemistry starting from the early 80s. And I just sketch you here the story. And so people found that you could do the following kind of low temperature trick. You could start with something that is easier or thermodynamically stable to grow, in this case, a perovskite version of the nickelates. I know many of you are also studying these sorts of systems. And you could do a series of deintercalation, oxygen deintercalation reactions where you pull out rows of oxygen and then the other row. And you could kind of collapse this structure down to what would be nominally nickel 1+. And so these are some of the key papers that we're building on. First, the discovery of this process in powder chemistry. And secondly, in the 2009, 2 key papers from Japan showing that you could do this in thin film form, right? So those 2 aspects we'll definitely build upon. So just to give you a sense of our neck of the woods, you have a number of experts in oxide thin film heterostructures in the audience here. And so we've been collectively getting pretty good at making fairly precise superlattices, interfaces, and heterostructures using various growth techniques. Both MBE and PLD are in the audience. So that's how we're going to grow this perovskite version of the nickel. And so that's kind of stainless steel, UHV, all that kind of business. The second step, this soft chemistry reduction, is rather cool and looks primitive, but it's very important. This is just a picture of how it looks like. This is a little piece of our thin film sealed in vacuum in a glass tube, and these are calcium hydride pebbles for a reducing agent, right? And so again, it's a low temperature game. This is like 250 to 300 degrees C, where we can kind of slide out the oxygen and maintain the structure to some degree. Right? That's why this language of topotactic the chemists have been using. Okay, so again, this is all games in metastable materials. It's quite a challenging chemistry to deal with. I will skip a lot of the details and just show you some pictures of 3 snapshots of the evolution. So with this hope of going after superconductivity, we spent a lot of energy taking something that was doped nominally, where you find the dome of superconductivity in the cuprates. And we see traces at the early stages of like a superconducting transition. And just wanted to show you that this was really kind of quite a messy material. It turns out this hint of a partial superconducting transition was a very narrow nanometer or 2 sliver at the interface. And it doesn't reproduce well here, but you can see this looks kind of like a mess, and that's the point. This is all secondary phases, decomposition products, and so forth. Okay. But of course, seeing this taste, we worked hard to try to stabilize this, and we could stabilize a little bit thicker in proximity to this substrate region, this infinite layer phase, and at that point achieve kind of full superconducting transitions in this material. So just to talk to you through the kind of materials challenges, this series of kind of chemistry reduction reactions requires you, in this particular case, to go to a very high, unusually high oxidation state of nickel, then reduce it to a very low oxidation state of nickel. And all the while, we're trying to keep this oriented on a substrate. And so this lattice constant is moving around by a few percent. Right? So that's the opportunity and challenge. But this hint that was already observed, by the way, before we had done this, that there's a proximity effect with respect to the substrate, was rather interesting. It seems to give you a director to say this is the plane orientation of oxygen to deintercalate. So the final step for us was to then take this proximity effect on either side of a sandwich of this material. So for a while, this was kind of a typical sample that we studied. We have this proximity effect, as I told you. And so the maximum single crystal thin films we can stabilize is about 100 angstroms, maybe 150 angstroms. So that is a big limitation, of course. The second thing I can mention is that I'll come back to this point. If your eyes are clever, you can kind of see extended defects, like shifts and rectangles in this field of view. And that is, again, an instability that we've been struggling to deal with. And I'll show you some progress in a moment. OK, so with that backdrop, we at least had something that was single phase, that we could kind of understand what we were measuring and studying. And so the first kind of series of data that we took was just looking at this comparison between an undoped perovskite nickelate and a doped version. So as I said, this is a very interesting system already in the perovskite form. It has this famous metal insulator transition associated with orbital and magnetic and all sorts of different kind of interacting order parameters. And if you dope this kind of material, nominally by whole doping, by substituting strontium for neodymium, you suppress all of this business and kind of have a moderately bad metal all the way down. So this guy is nominally starting from 7d electrons. Here's a cartoon of that kind of orbital structure. And now if we pull out from O3 to O2, this deintercalation reaction, you nominally go to now a D9 configuration. And what do we find? we find that this neodymium nickelate, now O2, is kind of neither a good metal or an insulator. It has this rough logarithmic upturn at low temperatures. But indeed, if we look at the dope compound, we see a nice superconducting transition, typically on the scale of 10 to 15 Kelvin or so. Okay. So there's been a lot done. I will just give you a survey of a couple of the issues. So immediately after this, we and now other people in the group, there's been a number of efforts around the world, finding both by PLD, MBE, and recently even sputtering techniques. It doesn't seem to matter in detail, that sort of business. But if you can stabilize this perovskite precursor in reasonably high quality and do this reduction chemistry, then you indeed can induce this superconducting phase. So looking at simple doping phase diagrams and rare earth variants, what we find is there's kind of a generalized dome of superconductivity, both in terms of the chemical potential, and in this case, the relevant degree of freedom was the C-axis spacing, following the different sizes of the rare earths. Okay, so I just wanted to highlight two of the interesting issues that people are finding. Again, there's this question of, does this have anything to do with cuprates? And of course, there's a lot of this importance given to magnetic excitations in that system and their stability or prominence even upon doping. And so we've been, again, restricted to these very tiny little samples, almost no volume, and we've been very reliant on really big advances in resonant inelastic X-ray scattering that allows us to probe these magnetic excitations. And so what we find, for example, this is kind of in green here, the intensity across high symmetry directions of the Brillouin zone. The point being is we do indeed find fluctuation spectra that's strongly dispersive and looks exactly like what you would see for a spin 1/2 antiferromagnetic lattice. Right? And so here are parameters that we derive. And this is quite similar, typically, let's say, 30% down from the scales of JUC in the cuprate problem. Okay. Now, of course, the other key difference or aspect here is that the excitations we see are strongly damped. And so we find aligned with it is larger than the experimental resolution. And to leading order, it looks very much like the spectra you would find in a doped cuprate. So our qualitative understanding is this, these electron pockets that I alluded to. The fact that we have this unusual electronic structure is probably giving us damping channels even for the nominally undoped end member. So that's one message here, is that we have strong magnetic fluctuations that seem to be prevalent in this system. The second thing that a number of groups have observed over the past year or so is kind of stripe or charge ordering signatures. And there are lots of details we don't understand, but in all cases that this is observed, we see a prominent 1/3 charge stripe. And it doesn't seem to disperse upon doping. It just suppresses and kind of disappears as one enters the superconducting dome. And so I just flash you here a summary from a review article of kind of a generalized cuprate phase diagram. And to draw attention to the fact that, of course, there are important differences. That's one of the games or interesting aspects that we're all studying. But one has a dome of superconductivity and very similar instabilities in the problem, right? So magnetic excitations that are proximate and some version of charge ordering or stripe instabilities as well. And so one can also ask, it doesn't actually take much to think about what are the questions to ask by analogy. What about the normal state? For example, phenomenology like the strange metal phase and whatnot. And so you would think that this is easy to measure, but that has actually been quite a challenge. And I can just give you a sense for that. Okay? The problem for our community is to probe what we think is intrinsic transport. If I go back to the type of view graph I showed you before, we are stabilizing this sandwich by a substrate and the same material on top. I show you here more explicitly in dotted yellow lines extended defects that were, I think, all growing or forming in these materials. And we think this is the cause of essentially factor of 100 or so variations in the scale of the resistivity and even the temperature dependence. So this is just our first few papers from various groups across the literature. You can see, actually quite interestingly, things like the superconducting dome and phase diagram are nominally quite similar, but the resistivity is really all over the map. So anyway, that was our premise, that the scattering induced by these kind of few nanometer scale extended defects was the key issue. And so let me tell you why they form. I told you that we're trying to do this transformation where the lattice has to kind of expand by about 3% through this deintercalation reaction. And so what that's saying is that at least our initial efforts were to grow this perovskite form heavily strained, right? And so we're basically trying to grow this on a lattice that wants to pull this apart by 2.5%, 3%. And a natural materials instability then is these sorts of extended defects that at this level, what I want to communicate is it's a way for the lattice to stretch itself out. Right? So we grow this thin film, we have all of these extended defects, and what we're finding is that when we do this fairly low temperature deintercalation reaction, the cation lattice basically doesn't change. Okay? So whatever we grew is still frozen in there. We can't anneal it out, if you will. So the logic of the substrate we had chosen initially, and much of the community, was to say, let's make the perovskite precursor very unhappy, but match essentially what we project would be the natural lattice constants of the infinite layer phase. And that was the strategy. But as I showed you, that we induce defects here that we can't get rid of. And so a next step might be to say, OK, maybe we can split the balance a little bit. Can we get to a range where we can kind of force stabilize and avoid these sorts of strain-dependent defect formations? Right? So that was the logic of moving to a different substrate that kind of splits this difference. And indeed, we can kind of grow very nice films where we don't see these sorts of apparent defect formation. And not a shock, actually, then if we look at a direct comparison of the same doping level, same thickness, and what have you, we see that the scale of the resistivity comes down quite a bit. In fact, superconductivity is enhanced. And so we think we're at kind of the first taste of looking at what intrinsic transport is doing. Now, there's still a lot of caveats, right? Fairly narrow thin films, so surface and interface scattering are still relevant, et cetera, et cetera. But hopefully a big step forward. And so let me just take one slide to give you a snapshot of some of the things we're finding. So this is looking across now a doping phase diagram using this kind of compromise in terms of the lattice strain. And this is a normalized slope of the resistivity, right? Just to give you a sense of things. So the first thing is the superconductivity, the superconducting dome has grown quite a bit, right? So TC is now pushing on the scale of 20 Kelvin or so. The dome has widened out. And actually, if I didn't label this and let's say get the TC up to here, this is almost identical to the 214 cuprate dome. Now, as far as the normal state is concerned, we also see quite similar phenomenology. We have a narrow range of T-linear resistivity near the peak of the dome. And as we go to the overdope region, we cross over to kind of a T-squared regime, which a lot of people have thought of as a signature of going to more of a normal metal or Fermi liquid phase. And we have a log upturn on the underdope side. Again, very similar to what you see in the cuprates. So this is a bit busy, but these are different snapshots. Let me just highlight one particular comparison. These two green and purple or blue curves are our data near the peak of the dome. And all of these red and orange curves are actually 214 cuprate single crystal data. And what's kind of remarkable is that, for example, if I make this comparison, the numerical slope is almost identical to what's found in that system with a slight increase in the residual resistivity that we find, right? So what we're finding is that there are actually quite similar aspects of the normal state transport in the nickelates, despite a rather different chemistry, some details that I haven't fully expanded on in this summary, but this multi-band electronic structure, a very different parent ground state, right? And different details in the orbital alignment. So this is certainly an interesting playground where people are starting to look at the dynamics and ultra-fast response. So hopefully this will be of interest to this community. So I want to tell you about a second and more recent, please. Yeah. Yeah, why not?
So the big electronic structure difference between these layered nickelates and the cuprates is the presence, at least if you believe density functional theory, of a band associated with, I guess, the rarer.
Yeah.
So what is your view of that? Is it really there? Is it affecting the properties? Because in all the standard theories, basically, it should make big time differences.
Right. So I think it's there. It's weak, but there are spectroscopic signatures by both X-ray and electron scattering where you can see a projection to, I forget, the M-edge or whatever. So there's a little tickle of things going around with doping. Computationally, it's expected that there will be systematic changes in hybridization as you go across the lanthanides. So I think it's clearly there experimentally. I would say that without being conclusive, there are signatures of multi-band transport with the caveat that we don't really experimentally know what the Fermi surface is and those details. So that I would say fairly aggressively. Whether this is like a small perturbation on the main problem or centrally important, I don't think I have an informed opinion. I think the questioner should have more of an informed opinion on that, right? Yeah.
Well, I certainly got theoretical opinions.
Facts
are facts. That's it.
Okay. Yeah. But I would say that it's clearly there experimentally, and we would estimate that this is, let's say, 10% of the 10% electrons, kind of densities in the electron channel. So they're there.
But that's already, okay, so let's discuss this offline, but that's already a big difference from electronic structure, which says that it should be like 50% or more.
Yeah. We're actually trying to get some numbers for you, but yeah, let's take that offline since it's not very well baked at this point.
Can I just ask
Sure.
more along these lines?
Mm-hmm.
So do you have any evidence for really like a condor-like renormalization of the mass of the carriers, or this would be just some multi-orbital?
Yeah, I think there's a heterogeneity of opinions. So people, Fuchung Zhang and colleagues early on noted this thing looks kind of condo-like, this log upturn on the underdoped side. In fact, there are papers floating around in the archive thinking about that. My maybe slightly uninformed opinion is to be biased against that in the following sense. We've done even very high field experiments. So this doesn't really move around even with aggressive magnetic fields. And so I would have expected these kind of condo singlet type of ideas to be responsive to that. And if one goes back and tries to think about kind of real numbers for condo scattering and their density, at least for me, it's not really very tight, that scenario. But I should say, like I said, there are strong opinions on the other side of that coin right now.
Okay, and I'm sorry to hold you up, but a last
Sure.
question. A little more than a month ago, there was a preprint from Chinese group
Okay.
about 80 Kelvin superconductivity in lanthanum-3 nickel-2.
Yeah.
Is that related to this, or is that just a completely different thing?
Yeah, no, very interesting story. Stimulating. So let me see. Their proposal is the following. Their nominal electron count is 7.5 d electrons. They got a bilayer. So theirs is actually closer to these quantum well ideas, right? Where you basically have bonding and, you do this sort of thing to get where you want to be. So yeah, very interesting. It would be another way to get a spun 1/2 system in the x squared minus y squared channel. So I'm getting recorded. So I have all sorts of speculations. I don't know how to interpret the other business, It's certainly very suggestive. As a non-high pressure guy, I'm a little bit worried about things like the abruptness of the magnetic signature. It smells to me more like a first order transition. And so something clearly interesting seems to be there. It's, I think, a step, at least for me cautiously, whether that's really superconductivity or some other ordering transition, I think possibly is but what I would say is that this should be accessible. So I don't think this is a slow roll. So people are probably doing this around the world. I think both the synthesis and the measurements, except for the high pressure, diamond andesite work, should be something that we'll hear a lot about soon. Yeah. Yeah. Okay, cool. Yeah, okay. So what I was going to tell you about next was, yeah, I think just stop me when I should stop. I think this is going to just go. So this layered structure is quite interesting, and as I told you, this story the chemist discovered in the nickelates was, I think, the first experiment or materials manifestation of this infinite layer structure. And of course, quite famously, in the early days of the cuprates, this, I think the nomenclature I'm just stealing from the layered cuprate version was found and found to be superconducting for a number of groups. And more recently, a layered iron version. Again, quite an interesting system, a spin-2 magnet. Anyway, so these guys are living here, there, and everywhere. So, right? So I can stabilize this for copper, for nickel, for iron. There's incomplete hints in the literature that manganese can do the same thing. And so we were interested in cobalt first. Well, it's there in the middle, so why not? But specifically, we had a question that was kind of the second story I wanted to tell you about. And so we were looking for a case where we could make kind of a Jahn-Teller lattice and ask whether there are analogies to what we already know about ordered Jahn-Teller effects in 3D systems, right? So that was the motivation. As usual, things were more interesting and complicated than we thought. But let me tell you the story. Yeah, so I learned about this from Andy, actually, right? So I was kicking around as a student at Bell Labs, working on manganites. And this has this famous story that it's a strong Jahn-Teller ion, and there's a lattice of them. And nature comes up with a very clever way to have nominally a volume-preserving Jahn-Teller distortion that is on every site. By taking a long axis alternating here, there, and everywhere, right? So our question was, can we use these 2D layered systems to do a square planar version of this, right? And so first thing you do is if you look at the orbital structure in a square planar coordination, it's a much lower symmetry setup. And so there's actually one degeneracy only to play with, right? This XZ, YZ story. But you could well imagine that I might have the same kind of instabilities projected into 2 dimensions, right? The so-called Q2 Jahn-Teller distortion, I can squeeze or pull this diamond. Right? Of course, even in the very first Jahn-Teller paper, this was one of the canonical kind of cases that they were talking about. But as far as I know, this hasn't really ever been seen experimentally in a clean planar geometry. So this is what we were naively thinking about. Maybe we're going to do a 2D version of this. And to make a long story short, to try to come up with this led us to calcium cobalt O2. So by now I'm going to say you're all experts at this deintercalation chemistry, play similar games. And again, as far as we understand, this is quite a metastable situation. But you can make very nicely, actually, an infinite layer lattice of cobalt O2 planes. Right? So maybe hard to see. This is the so-called Brown-Millerite structure. If any of you play with or know like battery or electrochemistry people, this is quite an important class of materials for them. So we can make a nice crystal thin film of this guy and pull out oxygen. As I'll show you, we did made this guy, but it's actually quite weird. This should have just been boring planes, but you see visually these vertical stripes here and there. Right? So there was quite a bit more going on than we initially expected. This is a very busy slide. I'll try to get to the main point in the next slide. But if we zoom in, this is all beautiful microscopy done by Michelle Smeaton at Cornell. The bottom line is that for the calcium and the cobalt sites, we see crazy things going on. We're seeing something like 1 angstrom scale displacements and splittings of these sites, right? So these are various high symmetry projections. There's no way you can digest this, but just to say, this should have been 1 column of atoms, but it's split into 2, right? This one looks brighter because everything's on the same site, right? These sorts of things. Of course, what's hard for us is that we're dealing with an oxide. Again, the same story, just a narrow sliver of a thin film. So trying to do oxygen refinements, we've been using primarily grazing incidence, synchrotron XRD, and bright field electron microscopy to try to piece together that refinement story. Right? So I can come back to this if there's interest, but let me just tell you the answer. So this is our understanding of the refined crystal structure of this new infinite layer system. It's kind of crazy, but some of the elements you can easily recognize. Let's look at this diamond here. This looks like it's perfectly Jahn-Teller happy, right? I want to break the XZ and the YZ symmetry. I pulled this guy like a diamond. And in fact, because I have no apical oxygen, it looks like the neighboring layers of calcium went for the ride, right? You can see this thing made a nice little rectangle. So this makes sense from a qualitative Jahn-Teller story. This makes sense. But all this other stuff is kind of surprising. So the way I could pose the question is, why is only 25% of the sites doing what we expected? And I think it has to do with this strong interlayer coupling. You know? So the point is that Jahn-Teller stabilization of this site has pulled the calcium lattice, but that's then frustrated by the next guy, right? I can't do this side by side because the calcium either needs to squish this way or that way, and apparently nature decides to do this rather complicated thing, right? So what I can say is one way to interpret the crystal structure is the following, that we started from a very simple high symmetry lattice, and the result of this kind of competition or frustration is to make an electric quadrupole set of distortions with which I can tile all space. Okay? Just another way to just talk about the structure. What's interesting then is if I talk to my DFT friends, if they do a full ab initio relaxation, they indeed get the right symmetry of distortions, but it's way, way smaller, right? By more than an order of magnitude. And if, however, they kind of forcibly take the experimentally refined lattice and then do electronic structure calculation, what you see is kind of hopefully that this looks like a trimer molecule. There's a projection of the x squared minus y squared band for cobalt. And so it's like I've made a little trimer molecule, another trimer, a trimer, and so forth. So this was quite surprising and interesting, but it kind of dovetails to a school of thought that at least for me, Daniel Komsky taught me about and has been a champion of these ideas, that if you look at a number of the oxide systems, there's quite a lot of, or a number of interesting categories where it's as if it's not really this kind of atomic picture, but they're kind of molecular crystals being formed. So there are famous examples, for example, of iridate systems. There's work from Bob Kava. Again, this is taking these basic ideas from a review article. But so if I now tell you, let's just take the fundamental unit of electronic structure is a trimer molecule rather than this atomic site, then we can actually go back to their kind of starting simple picture, that we apparently have a molecular basis from which I can have a simple ordered Jahn-Teller effect. Right? I'm not sure that that's really the right language or the kind of the basis that one should consider it, but certainly would be a one self-consistent interpretation. And so it's just at the early stages, but really I think an interesting system, you know, can we dope this? The excitation should be quite rich, right, along all the different channels that you all like to study. So that was story number 2. So I finally get to, I think, what I was asked to talk about, which is this effort going towards freestanding films. And so we've been trying to do this for decades. I started working on this at the University of Tokyo, but didn't really make much progress. But I think the motivation for all of you is simple enough, especially in this day and age, that, you know, we were working in oxide heterostructures, but intellectually there are very similar things people played with in compound semiconductors. Very exciting developments over the last decade, obviously, in van der Waals and layered and stacked systems. And so the question that we had been long interested in is whether we could come up with a geometry and opportunity to really mix and match with all these different materials families, is one. Was very interested in learning, as I'll show you, we've been piggybacking off the things people have played with, for example, in graphene, mechanical response. And I think finally, you know, it's obviously an interesting geometry for doing transmission mode experiments, right? So this is something that has been fairly challenging for ultrafast people in thin film, conventional thin film or bulk systems. So hopefully this will be a growth opportunity. Okay, so let me tell you a bit about freestanding films. Like everything else, you know, it's not a new idea. I think this is the first example I know of in the literature. So like in the 1950s, people found you could grow FCC metals on sodium chloride. It fits pretty nicely. And so this paper was growing nominally a single crystal gold film where they squirted water in the backside and left a freestanding membrane of gold and started to play with their mechanics. In fact, there are some commercial processes where people actually grow on salt crystals in order to release, let's say, fragile or metal membranes. Another school of thought over the past few decades is in compound semiconductors, right? Cases where there's fairly sophisticated ways to do things like differential etching. All those chemistries have been worked out. And so cases, for example, in 3.5s where, let's say, you can selectively etch an aluminum-rich algan layer and release, again, very nice single crystal membrane semiconductors or even devices. And lots of people playing with that as a way to integrate this with, you know, very different materials towards soft electronics, if you will, and so forth. Okay, so how about for oxides? It actually already does have a small but long history. So the first examples I'm aware of is starting from, I don't know, 25 odd years ago, where for certain cases where the film is so kind of chemically robust, you could just dissolve the entire substrate away, right? And so here are first reports along those lines. And then a group, I think in Italy, there's been a fairly extended effort to take two perovskites, so strontium titanate and a manganite, where they had developed a little bit of selective etch chemistries to try to play kind of MEMS analogous games in oxides. Right? So certainly there were some things there, but the challenge is that we certainly don't have the sophistication and the scale of the semiconductor world to try to develop all of these detailed chemistries. And so we've been thinking for a while about ways we could do this in as hopefully a general way as possible. And so this is actually one of my favorite stories that came out of our group, and definitely not my invention, to be clear. The story I'm going to tell you about starts with cement, actually. So, you know, cement like building material. It turns out that inside of most kind of commercial versions of cement, there's this few percent component known as tricalcium aluminate. This is a crystal structure. It looks kind of crazy, but you'll see already why it's useful for our purposes, because if I take a slice of this, a quarter of this unit cell, this fits nicely on the type of perovskites we grow. Okay? Now, what happens in cement is that you know, you get your bag of powder cement, you pour water in, this thing makes a hydrogarnet. So it kind of swells and fixes and binds all the other cement components. And what's interesting is that if you go from the calcium version that you find in cement, go to strontium or even further to barium, you get kind of a factor 20 to 50 each time enhancements in the solubility in water, right? Just going along with, let's say, their degree of covalency. So cool. So with this idea, we looked at first the strontium version of this. Find we can grow this pretty nicely, pretty flat, and the usual things that are important for us to try to grow precise heterostructures. And this is a first simple experiment where we've grown a few hundred nanometers of this strontium aluminate, dipped it for a second in water, and you can see it's just cleanly etched away. Okay? It's just dissolved off. Now, the reason why a 3D aluminate can be so easily solvated in water is that actually this structure can be thought of as composed of 6-member aluminum oxide rings, right? So you can dissolve this unit and get it out of the way. It's a very nice way to have kind of a residue-free hard mask is what we're finding. Okay. So that's the story in our nice dry UHV chamber. This is just some other layer to grow. But after we grow some heterostructure, this epitaxial layer can just be dissolved away in room temperature water. So kind of piggyback off of the 2D world. So using various elastomer or polymer supports and masks, just dunk the whole thing in water, dissolve this out, and then we can transfer these membranes to other places. So genuinely, I mean, like I said, we've been trying to do this in various ways. This was Dee's insight. He's now a faculty at USTC. And this is from his first paper where one of the key advantages, there are many headaches, is that if things go well, you can really get very large area membranes on the scale of a research substrate. So this is a millimeter scale bar. And you can do things like do the best of what hopefully we know what to do, heterostructures and superlattices, but then release that and play with them in this freestanding form. Okay. And so this has really grown to quite an interesting subfield. This is our relatively small group, but these are the things that we've been playing with already. So what I would say to those of you on the measurement side that are interested, if you've ever heard of a decent oxide thin film that has been grown, we might not be able to do it, but somebody in the world is probably making a very high quality membrane. And so it should be a great opportunity for the ultrafast community. But already we're playing with cuprates, magnets, ferroelectrics, and so forth. Right? So as I said, there's lots of things to do. I won't read them all. I would say there are lots of growth variations. It turns out that we're using pulse laser deposition. Those details don't seem to matter. There are examples of MBE and nowadays sputtering as well to play the same game as far as a soluble buffer layer. Other approaches such as this notion of graphene remote epitaxy also seems to work very nicely. And a whole slew of opportunities ranging from applied ideas. Can you integrate these sorts of oxides with silicon or gallium arsenide systems? Andrea is here. Very nice work on starting to play with, say, nanomechanical resonators and these sorts of opportunities. And we've been fooling around with different things. I wanted to just close by telling you, again, hopefully by analogy, some of the things that we're finding in the static regime that might be stimulating to think about their dynamical response. And so it all has to do with strain opportunities, right? So we know in our community, very interesting usage of strain as a probe of things like unconventional superconductors. My world is used very much lattice strain of substrates. And our question is, what are the opportunities with these sorts of membranes? So I'll just give you a few kind of examples of what can be done. So again, a lot of this is just trying to find different experimental approaches. What we found is that the oxides can be functionalized and stick really well on things like polyimide or Kapton, right? So their interface adhesion is very strong. I won't go into the details, but this seems to be, in retrospect, a very useful way to strain very aggressively without starting and propagating cracks. So here's an example of a membrane that we've stretched pretty aggressively in one direction. An important starting point for us was to say, okay, it's one thing to say that the far field, or macroscopically, we've stretched it. What about microscopically? And so using grazing incidence X-ray diffraction, we could really see that the nominal strain we see by a microscope really corresponds to stretching the lattice one for one. And we can get to very aggressive numbers, not always, but in some cases, right? What's interesting is that as far as the oxides we've played with, we kind of can't really, except for one or two cases, see plastic deformation. It's really stretch and then brittle fracture. And of course, if we grow thick membranes, it looks kind of like bulk single crystals, meaning at room temperature they fracture by a small fraction of a %. But if we make this kind of a sweet spot for us, it's like 5 to 10 nanometer thickness, we can really stretch and bend and play with these aggressively. Okay, let me try to wrap up. So this is a little bit older work. This was using a manganite membrane, taking advantage that we can make it very big and try to do kind of uniform strain transport experiments. This is biaxial strain geometry, where we could take the metal insulator transition, suppress it, and go into an insulating state. And so then one could play with biaxial strain, magnetic field, and temperature, and explore quite a wide and interesting phase diagram where we can encounter magnetic transitions. We suspect that this insulator is an antiferromagnet, but we couldn't experimentally really probe that yet. And so again, keeping in mind that a % strain energy is kind of, electron volt scale changes, right? So whenever you have competing phases in the issues that this community likes, this is a very interesting, I think, approach. Another example is, in this case, I'll give you an example of uniaxial strain. A lot of this community has been playing with the soft mode dynamics of strontium titanate. Here we stretch in one direction. We're using piezo force microscopy. Basically, we see nothing, nothing, nothing at room temperature, and suddenly above a critical strain, you can see the induction of ferroelectric domains in their response. Right? And so, again, a lovely system. Obviously, we knew where to look because people had previously shown you're very close to this ferroelectric instability. In this case, HWANG was using second harmonic generation to kind of probe this a little bit usefully for a wide range of temperatures. And so we can really go from basically 0 to, we extrapolate to about 500 degree Kelvin, or 500 Kelvin ferroelectric transitions by about 2.5% strain. So again, a fairly flexible platform. Again, you can cut me off. My last topic in this vein is things that actually we're just at the beginning stages but quite interested in. Is we've done a lot of things with coplanar strain, but we're starting to look at bending response and trying to do this somewhat seriously. So as a brief introduction, if I have a simple linear elasticity theory and I give you some geometry, the bottom line story is that if in the elastic regime, Young's modulus and the Poisson's ratio can determine everything about how this would deform upon various loadings, right? So it's a very simple form for the free energy. And at least since the 1960s, if not before, people have thought about the question of what happens if there is a higher order term in that elastic energy. And so namely, if I had a term that goes as a strain gradient, then there should be some interesting consequences. The reality is this is hopelessly small, okay, in bulk. And for some of you, I think I know, do these experiments. This has been a challenging experiment. But the simple story is by going from a bulk crystal to a very thin floppy membrane, these sorts of gradient terms scale very favorably, right? They scale as 1 over the thickness squared, so that even for the same kind of bulk coefficients, this becomes a dominant term. And you can hopefully see this. This is kind of cool to me. This was an accident. This is a strontium titanate membrane, maybe 3-4 nanometers thick, and it kind of folded over. It looks like a piece of cloth, right? And these are silicon nitride 2-micron holes. And so it's that degree of freedom that seems very interesting if we can harness that and probe this in a controlled way. Okay, so I will quickly then summarize the first story where we find something definitively interesting or unexpected, let's say, coming from this gradient term. And that's, again, taking the things that people did in like playing with the nanomechanics of graphene. And so this is a simple drum head. And these colors show you that if I poke in the middle of my drum head trampoline, that the elastic energy initially is dominated by a bending response, right? It's the bending rigidity that's relevant. But if I poke harder and harder and harder, more and more of that energy is coming from stretching the material in between. Right? So that's the kind of story in terms of experimental response. This is actually real data. If I do an experiment where I poke a drumhead membrane, I can access a nonlinear regime, and I can start to trick out all of these coefficients. Namely, I can look at the Young's modulus, the pretension, and importantly, we're finding big differences in the thin limit between the Young's modulus for linear and cubic, the nonlinear response. Okay, I can come back to this if someone's massively interested. So here's the bottom line. This is just a series of strontium titanate membranes that we went from thick to thin. And we've tried to measure the Young's modulus. When it's very thick, we can only experimentally access the linear response. And we see something that's fairly universal, that we see from the bulk value a softening of the Young's modulus. But then we find something very strange. The linear response does a U-turn, and we have a huge, then, or relatively large splitting between the linear and cubic response. Another way to say that is simply look at this picture. What we're finding is in this thin regime below about 20 nanometers, this single crystal thin film of strontium titanate is about 3 times harder to bend than it is to stretch. Kind of looks like this toy, right? I can, it's a bit rigid in the bending rigidity, but I can easily, stretch this out and play this game. Okay. So I think that's the heart, or our best attempt at a clean experimental probe of this phenomenon. What do we think is happening? There's all sorts of things that could happen. I think my time's up. We suspect that what we're seeing is a dominance of the flexoelectric contribution, the polarization that we induce upon bending. And again, the bottom line story is this gradient term scales very favorably with thickness. So even if it's kind of negligible in a bulk crystal, you can blow it up kind of arbitrarily big if you make a skinny geometry. And our field is starting to play all sorts of games, right? This is barium titanate, and it looks ridiculous. You can bend it and flop it around, and lots of questions about the nanomechanical response in the presence of these sorts of induced or pre-existing dipoles. Okay. So I'm going to stop there and just try to tell you about 3 stories. They're all actually metastable in some sense, but very slow. Nickelate superconductors, and really finding that this kind of combined chemistry thin film approach seems like a fairly rich playground to uncover new quantum materials. And both of these, as well as this membrane geometry, really seems to host a lot of the instabilities that you folks care about. And it might be a very nice way to fine-tune or get close in the parameter space that you had introduced in the kickoff. So let me stop there, and thank you very much.